Now we are going to talk about the behavior of magnetic dipoles inside magnetic fields. For this purpose, I'm just going to provide this definition in here. A magnetic dipole is any kind of a physical system that has a magnetic dipole moment. Right? A circuit, a current carrying circuit, is an example of this. And inside atoms, of course, the electrons are moving around the atomic nuclei, and so therefore they correspond to some kind of a current, and they also have a magnetic dipole moment. In that case, of course, there is no circuit, but there is a current distribution. So as a result, in nature, of course, we meet these kind of current distributions somehow, and so as a result, we just call them as magnetic dipole. Why do we call them as dipole? I'm going to talk about this later, but not right now. So when this kind of a physical system is placed inside a uniform magnetic field, when a dipole is placed inside a uniform magnetic field, let's remember that this magnetic field is external. Some other charges produce this magnetic field. Then we have these two statements that the net force should be zero. The net force is zero. But there's a net torque which is given by the cross product mu cross b. This is the place where magnetic dipole moment actually enters into the equation. So we basically define the magnetic dipole moment by using this equation as the basis. So that's the you can think of this as a definition. And then, of course, by solving the previous problem, we have shown that this magnetic dipole moment can be expressed as the current multiplied with the area. All right, let's just remark in here that if the magnetic field is non-uniform, it is possible that there can be a net force. So that's a possibility. But of course, I'm not going to provide any formula for this. But when we talk about the energy, we can then talk about these. So at this point, I'm just going to use this mu cross b expression to describe the behavior of the magnetic dipole inside a magnetic field. So since I don't care what the physical system is, I don't care about how the currents are distributed. I'm only interested in the magnetic dipole moment. So mu is the one that I'm going to describe. There's something complicated going on in here, but as I said, I don't care. All right? There's a uniform magnetic field in space, so there is a magnetic field like that. The magnetic field is like this. And of course, in general, there's an angle between these two vectors. I'm just going to describe this angle like that. So as a result, since angle is defined like that, this angle is always between 0 and 180 degrees. But if you want, you can also define these for negative angles as well. But when time comes, of course, we can also treat these kind of things. So you can see that the torque in here is mu cross b, right? Mu cross b. So as a result, this magnetic dipole, at least the magnetic dipole moment, will tend to rotate in a direction which makes it parallel to the magnetic field. So let me just draw a few cases in here. I'm just going to draw this striation, that striation, and that striation. So I'm going to use the yellow colors for the magnetic field always. So this is the magnetic field, and the white is the magnetic dipole moment. So in any case, in all of these pictures, I'm going to have this. So as a result, for the first case, for this one, right, for the first case, mu cross b, the torque vector is pointing out of the screen, so the torque is out of the screen direction, so therefore the rotation is along that direction. For the second case, this one, magnetic dipole moment is aligned parallel to the magnetic field, so therefore the torque is zero, no torque in here, so it's going to stay there. And finally, for this situation, if you just compute the torque, right, for the case where both of these vectors are within the plane of the screen, in that case the torque vector is pointing into the board, so therefore the rotation, the dipole would be rotated, would be forced to rotate along this direction. So you can see that in all of these cases, the dipole moment vector tries to be parallel to the magnetic field, so it just wants to orient along that direction. So this kind of tells us that the this orientation in here is the stable equilibrium position. This is stable equilibrium. Instead of position, I'm going to say orientation because we are talking about angular positions in here. We have the opposite extreme. Of course, I'm going to first draw the magnetic fields like that. Right? So if I have my magnetic dipole moment pointing exactly opposite, in that case too, the magnetic dipole moment and the magnetic field are anti-parallel, so therefore the torque on the dipole is 0. But this is unstable because if the dipole is slightly off from this orientation, in that case, for example, by using the right-hand rule, you can see that the torque is pointing into the screen, so therefore this is going to rotate like that. So as a result, the dipole will basically get removed from this equilibrium orientation. Right? So therefore this is an unstable equilibrium. You can see that it doesn't matter if the dipole moment is like that. So therefore in that case mu cross B is going to be out of the screen, and so therefore this is going to get rotated like that. So as a result, if the dipole somehow gets away from this orientation, in that case the torque will be in a direction which will remove the orientation even further from this, and so as a result this is actually an unstable equilibrium. All right. So as a result, for all other orientations as well, you can see that the torque is always in a direction which tends to make the magnetic dipole moment parallel to the magnetic field. Okay, one example is the compass. Compass is it's actually hard to show that the definition that we have provided. Let me draw this correctly. Is also valid for the compass as well, but as I said, I'm going to talk about this later on. So compass needle is something like this, and there's a magnetic field, the Earth's magnetic field, right? I don't know, it's along this direction, let's say. But this compass needle is actually a complicated physical object, but I can express this as a magnetic dipole moment quantity. So in that case too, the magnetic dipole moment tries to orient with the magnetic field, and that's basically what we see. So as a result, this is what we usually describe the motion of the compass needle, for example. Let's say that the initial orientation of the compass needle is something like that. This is mu, right? Let's say that the initial kinetic energy is equal to 0. This is starting from rest. In that case, we will see that there's a torque on the compass needle. So as a result, the needle is going to rotate like that. So as a result, eventually, of course, it's going to get oriented parallel to the magnetic field. But in that case, it will have a non-zero kinetic energy. So at that orientation, the kinetic energy will be non-zero, which means it is still moving with, it has an angular velocity. So therefore, it will pass that orientation. So as a result, it will swing like that. So you can kind of see what can happen in here. This is going to basically get swing back and forth like that in here. So with friction, of course, the swinging will slow down, and eventually you are going to find the magnetic dipole moment to be oriented exactly parallel to the magnetic field. This is just like pendulum. All right, I'm just going to make a similarity in here. Let's remember the pendulum in here. There is a gravity in here which plays the role of the magnetic field. And there's pendulum in here. This vector plays the role of the dipole moment, whatever. So the pendulum does the swinging motion, and with friction, of course, it slows down. Eventually, we are going to find the pendulum in the orientation where this vector is pointing parallel to the gravity vector. Right? We have exactly the same kind of situation in here, except that the quantities and their physical meanings are different. So we have a magnetic field, external magnetic field, and a magnetic dipole moment, which are the relevant vectors. Their equilibrium orientation are as shown. Okay, so the next thing is about the energy. So let's then talk about the energy in here. All right, I'm going to draw the pictures again. So that's the magnetic field. And that's the magnetic dipole moment. This time I'm going to choose the angle properly, so that angle is this. So therefore, angles along the direction of the arrow would be counted as positive. That orientation would correspond to zero angle, and these orientations would correspond to negative angles, right? Let's just keep this in mind. So what is torque? Torque is a vector which is pointing, in this case, out of the board. So therefore, let's just express the torque in the out of the board direction. So this is given as mu b times sine theta. Right? When angle is measured with that arrow, and the torque is measured along this out of the screen direction, in that case, these two formulas are consistent, and they have consistent signs, so therefore I can use for this for any angle, for negative as well as positive angles. So when theta is positive, the torque along that direction is positive. When theta is negative, then the torque along that direction is negative. So that's kind of consistent. Next thing is the, well, we can talk about the energy. So work done by the torque. So that's basically the magnetic work done. Work done by the external magnetic field. Let's say it like this: magnetic work done by external field. Let's remember the directions again. So work done is on any small processes, the torque dotted with the displacement, in that case theta. I'm going to call this as d theta. Right, there's always a confusion about the directions in here, but let me just say this. D theta is basically a vector which is whose magnitude is basically d theta multiplied with a direction which is, let's say it like this, it's a unit vector which is into the board direction. So let me call this as n. So that means n is a unit vector which is pointing into the board, and this theta is essentially, as a vector, is equal to theta times n. So that's going to give us the correct three-dimensional direction for the vector. And the torque is, well, torque has a component, tau, which is given in here, and its direction is in the out of the board direction. So I'm basically computing the out of the board component of this. So as a result, I'm taking the dot product of these two. So let me erase this extra dot in here, which is meaningless. All right. So as a result, I mean, these vectors are actually vectors along these directions. So d theta is into the board with a component d theta shown in here, and the torque is an out of the board with direction with component tau that's shown in here. So as a result, this is tau times d theta, the dot product of m with n, m dot n. Since these two are opposites, so this is actually negative. All right? Which means if I compute the work done in a process where the angle changes from I to F, then in that case I need to integrate this from I to F. Right, and in that case I can write down the expression in here. So this is mu b sine theta d theta. Sine theta has an integral which is minus cosine theta. So therefore the integral is mu b cosine theta with that difference. So therefore this is mu b times cosine theta f minus mu b times cosine theta I. Right. This is a conservative work done actually. Work done depends only on the final orientation angle and the initial orientation angle, so it doesn't depend on the path. So as a result, I can then define a potential energy. So this is the magnetic potential energy if you want. So the work done is equal to the negative of the change in the potential energy. So this is the final magnetic potential energy minus the initial one. So you can see from here that we have to define the magnetic potential energy as minus mu b times cosine theta. Plus a constant, but we forget about the constant. We can express this formula by using the vector nature of the two vectors involved. It's just a dot product of these two vectors. So let me show them again in here. So this is the magnetic field, and that's the magnetic dipole moment vector, and theta is the angle between them. So I can then express the magnetic energy as minus mu dot b. All right, from here you can clearly see that the stable equilibrium orientation, which corresponds to the minimum potential energy, so that's stable equilibrium, corresponds to potential energy being minimum, in which case the minimum potential energy happens when the two vectors are parallel to each other. So when these two vectors are parallel to each other, we get the minimum energy because of this negative sign in front. And we have unstable equilibrium when the potential energy is maximum. So in that case, the maximum value is equal to mu times b. This happens when these two vectors are anti-parallel to each other. Let's again remember the vector nature of things. Energy is a scalar quantity, and we would like to express it in terms of the product of two vectors. One is a dipole moment vector, the other one is the magnetic field vector. So to be able to obtain a scalar quantity by multiplying two vectors, I need to use a dot product in here. So that's why we need a dot product in here. But on the other hand, for the torque expression, the torque is a vector. This is also a product of the magnetic dipole moment and the magnetic field. But this time the result is a vector, so therefore in that case I have to multiply. I have to use the cross product in here that produces a vector. So that's basically the distinction between the energy and the torque. They have the same units, it's Newton meters, but of course they are different concepts. One is a vector that shows some certain direction of rotation, and the other one is a scalar quantity. So it's not a surprising thing that both of the expressions are just the product of these two vectors, magnetic dipole and the magnetic field. But since the nature of these two quantities are different, we use a different product in here. So we have a dot product and a cross product. Let's just remember these. This is actually this is a very important distinction. All right, let's then talk about the similarity and the difference with the electric dipoles. I'm not going to talk about the difference in here, so I'll just talk about the similarity. First, let's talk about the definitions in here. So in the case of electric dipoles, if you remember, we have defined dipole as any charge distribution where the total charge is zero, but there's some kind of a separation between negative and the positive charges. So in that case, there's this geometric quantity, which is the distance between these two charges. This is a vector, so that's a distance vector. And there's a electrical quantity which corresponds to the charge on these charges. So electric dipole moment is defined as the product of the charge with the geometric quantity. Let's just remember this, and we have a similar parallel for the magnetic dipole. In that case, we have a current, which is the electrical phenomenon in here, a current in space, which is distributed in space, and a geometric quantity, which is the area, which we take as the vector in here, right? So in both cases, the geometrical quantity that describes how distributed these things are is a vector. So the magnetic dipole moment is the product of the electrical quantity, which is a scalar, multiplied with the geometrical quantity, which is a vector. So there is a parallel in there, but of course, just keep in mind that the units are different. So, so the two quantities are entirely different from each other. But we also see the same behavior inside a uniform field. So inside a uniform electric field, net force was zero, and there was a net torque that I could express in terms of the dipole moment. And as a result, we were talking about some potential energy. We have derived this potential energy in alternative waves. These are actually given as the cross product and the dot product with a negative sign. We have the same situation inside a uniform magnetic field, right? So the net force is zero, net torque is given by the cross product, and the potential energy is given by the dot product with a negative sign. So as a result, there is a complete parallel between the formulas. And so as a result, there is also a complete parallel between the equilibrium orientation. So because of the essentially potential energy expression, you can see that the stable equilibrium, which corresponds to the minimum potential energy, corresponds to the orientation where these two vectors are parallel to each other. And it's similarly for the magnetic dipole. So since the potential energy expression is the same, when the dipole moment is parallel to the magnetic field, we have the minimum energy orientation, which corresponds to the stable equilibrium. All right. So next, let me briefly try to answer that obvious contradiction. So we have said that we have said this as a general rule, that the magnetic forces do not do any work on charged particles. But somehow we have talked about a magnetic potential energy in here. So the magnetic potential energy is just the you just define by using the work concept, of course. Work done by the magnetic field is equal to the change in the negative of the change in the potential energy. We just define it like that. So as a result, it appears that at least for the case of magnetic dipoles, the magnetic forces actually do any work, do some work, right? That's the reason why there's a magnetic potential energy. So the question is why, how do we resolve that contradiction? So was the statement that the magnetic forces do not do any work was unnecessarily too general? If you think about it, there is nothing physically new in here for the magnetic dipoles. Actually, we are talking about the currents, which are moving charges inside wires. So as a result, the statement that we have made about the magnetic forces doing no work on moving charges should also be valid for these kind of cases too. In any case, I'm going to give the answer like that, but I cannot give the full answer right now. What we have said when we talked about the magnetic forces, that the magnetic forces cannot directly exchange energy with the charged particles. That's the key word in there. So the magnetic forces can actually exchange energy, but we are going to see this later. There's a process called induction, where if you change the magnetic field, it just produces an electric field, and those electric fields can exchange energy with the particles. So there's some kind of a intermediate process in here. So I'll just quickly describe in here. So there's a process called induction. So let me try to describe it like that. We have a current carrying loop in here, and there's a magnetic field in here. Let's say there's a magnetic field in here. So if I try to rotate this rotate the loop, the current carrying wire, it appears that there's an electric field produced in here. And this electric field, there's an extra induced electric field in here. This electric field does work on these charge carriers. So as a result, it's not a work done directly by the magnetic fields. It's not that. But it's a work done indirectly by the magnetic field. So somehow first the magnetic field produces this induced electric field, and that induced electric field does work on the charge carriers, right? There's an indirect process. So as a result, I mean, the final conclusion is that, well, there's no contradiction between these two statements, right? There is actually a potential energy. We can talk about the potential energy of magnetic dipoles when they are placed inside magnetic fields. We can use this potential energy to discuss physics. There is nothing wrong with this. But the first statement is also the correct one. So we can safely say that the magnetic forces somehow do not directly exchange energy with the electric charges, but indirectly they can exchange energy. But in that case, there are some other processes that we have to take into account. Obviously, it is too early to talk about this induction process in here. So as a result, when time comes, we can revisit this problem.